here I have a line. I've picked two x values, x1 and x2, corresponding y values, y1, y2, and hopefully this picture looks familiar to you. What comes to your mind when you see this? Nathan?
I want to find the slope of it.
Slope, right? So what is the formula, Nathan?
I want to do y2 minus y1 equals x2 minus x1.
Okay, very good. Paid attention in algebra. Formula of slope, and we want to know how much the line slopes, and to find that magnitude we end up computing this value. So prior to, say, college algebra, middle school, high school, they might have used two words that start with the letter R to explain this. Louder, Jane. Rise over run. Run part. Rise part. Back when you were a baby man, slowly you grew up. You ended up doing this, which is the slope. We're all growing up toward that. So another step, slowly but steadily. Next step is to see this in a different way. Can I say that when I have y2 and y1, you made a change and got to y2? Yes or no? Say if y1 is 5, y2 is 9, there is a change. Y changed from 5 to 9. So instead of simply calling it as y2 minus y1, I'm going to call it as change in y. Take a guess, what should the denominator be? Change in x. Good. Something divided by something else, we could call it as a rate. You agree? Okay, I've got two changes. I'm going to give it a name, rate of change. So, baby steps. So back when middle school, maybe college, here you are in calculus, rate of change. But it all goes back to basic slope. Okay, change in y, change in x, still a bit too complicated. In terms of writing, mathematicians, statisticians, we like to be effective. I don't want to waste time writing stuff. So to denote change, we use delta. Delta y divided by delta x. So change in y with respect to change in x. How does y change when you change x? Hence, rate of change. And we have delta to denote the change part. Okay, this average rate of change happens on an interval between x1 and x2, correct? So over this range of x values, the corresponding change in y values is that. Since you have a whole range of values, and you're trying to find the rate of change, we like to call this average rate of change. Good. Should make sense in this problem easily, because if I asked you, well, how much does the line slope over there? What would your answer be? Let's just say that the slope is 2. What is the slope right there? Slope of that line is 2. Perhaps I draw it in a different color. What is the slope of that red line?
2.
Can't hear you. 2. Let's make that red line a bit longer. What is the slope of that line?
2.
2. What is the slope of that line?
2.
That line.
2.
That line. Okay, the entire line. Entire blue and red line. 2. So when you have a line, no matter what piece you take, you would always have 2 as the rate of change. But by all means, it is the average of all those slopes. Agreed? 2 plus 2 plus 2 plus 2 plus 2, 5 2's added together, take the average, you end up getting 2. Average rate of change. Okay. Food for thought. I will get into detail, but just think about this. So the squiggly curve is what I'm studying. So I drew this line. I'm going to find the slope of that line. Is that slope going to be positive? Yes. So that is going to tell me that over this interval, the average rate of change is positive. So the function that is a curve is increasing over that interval. But is the function just going up, or is it going up, then down, then up? Okay, so it is a bad idea to use the average rate of change to understand something about this function. Do you agree? Because the average rate of change is telling me, oh, it's just going up. But in reality, it's not just going up, it's going up, then down, back up. So average rate of change is not good enough to understand functions. Okay? So good place to stop.